We are now into chapter 9, and we're using t-testing for independent samples, also known as the independent samples t-test. I also call it, in shortest form, independent t-test. So all of those basically mean the same thing, and this is referring to chapter 9 in your textbook. So let's talk about when we would use or why we would use independent measures or independent subjects t-test. Um, an independent t-test falls under the category of what's called a between subjects design. So the t-test is a hypothesis test, a statistical analysis that is within a between subjects design. So that's how the research design is created. And between subjects design just means there's different participants observed in each condition or group. So there's, for t-test, there's two groups. There are different people in each of those groups or each of those conditions. Often when we think about those groups or the independent variable, which distinguishes those conditions, we use the term factor with between subjects designs. When we start getting into more of the advanced designs like an independent t-test, because factor, it basically is a term that's used for either an independent variable or a quasi-independent variable with, and it can mean that there are different levels in that. So we could be looking at more than one independent variable when we're talking about between subjects design. So for example, in this example, we can see we're looking at gender as one variable. So that's the first variable. But on the other variable, we're looking at personality. So that's like the second variable. So that instead of saying there's two independent variables, or two quasi-independent variables, we often just say there's two factors. So those are kind of used interchangeably when we're talking about between subjects designs. So with an independent t-test, you only have one factor or one independent variable or quasi-independent variable. You don't have two. Two goes beyond the scope of this class. So lucky for you, you don't have to learn how to calculate anything with more than one factor. So the independent measures design or the independent t-test basically is that research analysis, a statistical analysis that compares the means or the differences between the means of two separate groups, or two separate conditions with different participants in each of those conditions. Meaning, I might be in the first condition, but I'm not in the second condition. There's different people in the second condition. So it's used there's different terms for this. It could be called independent measures design and independent subjects design, a two independent samples t-test. I always just refer to it in the shortest form possible as an independent t-test. So just looking at the differences between those two conditions. And in reality, it's just like the typical hypotheses. We are inferring from the samples to the population. So we're inferring that our sample differences are going to reflect what we would see in the population if we looked at the population differences. So we're talking about two conditions, two means, and the differences between those two. So there are things that we need to assure before we can report results, or we often have to take them into consideration. And remember, on the one sample t-test, we looked at assumptions as well. We also have assumptions for the independent t-test. In the independent t-test, we have three different assumptions. We have normality, we have independence, and we have a homogeneity of variance. So if you remember, normality is just either you're sampling 30 or more participants, so to make sure that that sample size is large enough, or we know that the samples that are being taken from the population, that those populations they're taken from are normal. So there's two ways you can meet normality. Independence, that's assured within the independent measures because the people in condition one are different from the people in condition two. So the people are not going to influence each other's scores. Um, my score, if I'm in the second condition, is not being influenced by anyone's score in the first condition. So the results, each score or each result is independent of all the others. It's a separate entity. I don't have people in the same people in each of those conditions because that would influence the results. The third one is homogeneity of variance. And homogeneity of variance is your newest one. It just talks about that we're assuming that the variances are not significantly different. So, homogeneity of variance is also known as equal variance. But in reality, we are not looking for exactly equal variances between the conditions. Is what we're looking for them is to not be significantly different. So we actually have to test for homogeneity of variance. If we don't meet these assumptions, then more than likely our results are invalid. So that's just to kind of let you know how the independent measure t-test is influenced by these factors when we're designing research analysis for testing a hypothesis in a study. So hopefully by now you know step one is to state the hypotheses. Um, Step two is setting the criteria. It's going to look a little bit different for independent t-test because now we have two samples. And we don't have a population. We're inferring about the population. So is what we need to do is take the degrees of freedom for each sample and add them together. So there's a few different ways of doing that. This would be the degrees of freedom for sample one. You add that to the degrees of freedom for sample two to get the total degrees of freedom. That's what you're going to use to look in that critical distribution table to kind of look and see what that critical value is based upon that degrees of freedom. So now it's not just one sample you're accounting for, it's two samples, two different degrees of freedom that you will be utilizing to create that critical boundary to set the criteria for the decision. And we will go through these steps, don't worry. I'm just kind of uh, teaching you the new information for independent t-test before we dig into everything. So information that has changed dramatically from the one sample t-test. So here is the test statistic for the independent measures t-test or for the independent t-test. Is you'll notice in the numerator, it's the t obtained basically. It's the sample mean for the first group minus the sample mean for the second group, divided by, and this is a notation. This whole thing is a notation. And it's the estimated standard error of the mean difference. So this is equivalent to SEM when we did z-test or S subtext M when we did one sample T, but now we're looking for the estimated standard error of the mean differences. This is not an equation. You're not subtracting means. This is just a notation. There's some steps that has to be done to get to that equation. So this is the final step, that t statistic, to get that t obtained. And remember, this just measures the number of standard deviations that a sample mean shifted from the population mean, or the sample mean difference shifted from the mean difference as stated by the null. And for an independent measures t-test, because you're looking at two samples, if the null is true, the difference between the two samples would be zero. There would be no difference. So really the null is zero when we're talking about the independent t-test. So here's kind of the steps that we're going to need to get to that estimated standard error. So here is that notation again. This is the actual equation. And is what this is this right here is our pooled variance and a pooled variance. And this is sample size and sample size. If you'll notice, these are two separate fractions being added together. There is not a line through. So It is not this. It is not that. And adding, it is absolutely not that. It is simply two fractions. So this is a fraction that you're adding to this fraction is what that is. It's very important to know. But you need to learn how to get the pooled variance. If you remember way back in chapter 3, we learned how to get the weighted mean. Basically, the pooled variance is a weighted variance, is what it is. So it's the average of the two sample variances in reality. So um, what we need to do is get the sums of squares for each individual group. So if you recall, sums of squares equation is just the sum of x squared minus the sum of x total squared divided by n. So you would need to do this for the first group, and then you would need to do it for the second group. So there might be a treatment condition and a control group. You're going to have to do that for each group. And then, so all of that is divided by the degrees of freedom added together. This is where I would suggest you put parentheses around this numerator and then parentheses around the denominator to make sure that you're getting the appropriate information. Now, if you're given variances, you would take the variance and multiply it by the degrees of freedom, its corresponding degrees of freedom, and then add that to the second condition's variance times the degrees of freedom and divide by the degrees of freedom combined. Remember, variance is the sums of squares divided by degrees of freedom. So S squared and SS are two different things. You have to have SS to get S squared. So it's basically, if we had this variance and we had this degrees of freedom, we could solve the sums of square by multiplying these together. And that's really what's happening right here. That's only if you're given the variance instead of sums of square, which you might be on the exam just to help speed things up so that you are not having to calculate sums of square from scratch. So it's just for you to be aware that S squared and sums of square, the SS and S squared are two different things. So here's an example study. So, and your next application activity is going to go through this. So hopefully this will help you complete that application activity. So in this research study, they believe a new therapy technique will decrease depression more than the traditional cognitive therapy. And so this word decrease is suggesting a one-tell, right? And so when we set up research studies, the group 1 should usually be the experimental group or the treatment group. And group 2, it is basically your control condition or what is already known. So in this case, group 1 is the new therapy. Group 2 is that traditional cognitive therapy. So the group 1 is what we are predicting to differ in one way or another. And this way specifically, decrease. If you go through this, you'll notice the new therapy technique, that's our independent variable, or the therapy technique is our independent variable. Our dependent variable is the depression. That's the outcome, the dependent variable, to help you out to get those hypotheses going. So step 1 is just stating our hypotheses. So the null is that the new therapy will not decrease depression more than the traditional cognitive therapy. The alternative is the new therapy will decrease depression more than traditional cognitive therapy. Again, remember, hypotheses are not questions. That there is the alternative hypothesis, which is a prediction, and the null hypothesis is what we believe to be true until that's disproven. So it's never questions when you're talking about your hypotheses. If your hypothesis, either of your hypotheses are stated as a question, it will not get credit, unfortunately, because a hypothesis is not a question. A hypothesis is built off of a theory, which sometimes is influenced by a question, but the hypothesis itself is not a question. So step one is done. Now we can go to step two. In that original data set, we had 5 in each condition, if you recall. So if we took the degrees of freedom for each group, basically, it would look like we would have, 5 minus 1 plus 5 minus 1. So that would be 4 plus 4. So degrees of freedom is 4 plus 4, right? So our degrees of freedom is 8. We would go into that T distribution table, if you recall, that we're using. I'm sorry, I popped out of the scene. I thought it was a unit normal table, but it's at the back of your textbook. It's the T distribution table. It's still the same one that you use for the one sample T. And in your textbook, it's page 297. You're going to go and find the degrees of freedom of 8. And because we're going to use a 0.05 and it's 1 tel, we're going to find 0.05 under 1 tel. And we're going to go down and look, and you should get 1.860. But you're going to need to make it sure to put a negative in front of that because we are looking for our depression levels to decrease. So that critical value would be negative 1.860. So a nice way to kind of visualize this is here's your distribution. And now we're going to, right here is our boundary, which is negative 1.86. Anything beyond that is significant, okay? So, and that means when your T obtained is further out, the absolute value is larger. So don't compare, like if your T obtained is 2, negative 2, and this is 1.86, don't think of, oh, well, negative 2 is lower number than negative 1. It's further in the tel. So drop those negatives so you can compare just the values without the sign when you're comparing your obtain to your critical boundary. So here's just the basic information that we're going to need to calculate our independent t-tests. So at the very beginning, here's our obtained test statistic here, okay? Our basic calculations that we're going to need is we're going to need the sum of x for group 1. So that means adding up just 42 plus 37 plus 42 plus 36 plus 34. The sum of x squared for group 1, that means 42 squared plus 37 squared plus 42 squared plus 36 squared plus 34 squared. You're going to find the sample mean for group 1 and the sums of squares for group 1. You have to do the same exact thing for group 2. So each of these groups are going to be, these calculations are going to be separate for each of those groups. And those are all the basic calculations you'll need. So let's get started on kind of what is needed to plug into this equation for the test statistic. So let's start with our sums of x's, that first step, so that we can get our means. If I were you, because we're going to be needing a lot of this information over and over again. So if you just get your mean, then you realize, oh, and 2 more steps you're going to need to get the sums of squares. You don't want to have to recalculate this all over again. Is what I would do is make a legend and write down the information that you have. So I have like sum of x1 for group 1 is 191. Sum of x2 for group 2 is 204. So that you can always go back and grab those numbers and you don't have to recalculate or anything, or you don't have to scroll through your calculator and risk accidentally pulling the wrong number for the wrong information. So when we plug these in, our sample mean for group 1 is 38.2. Our sample mean for group 2 is 40.08. And now we have the numerator set up, ready to go, okay? But now we need to work on getting our estimated error of the mean differences, our standard error of the mean differences. So to start that process, we're going to need to get our sums of squares. So if you remember, so we're going to have to get our pooled variance before we can get our estimated standard error. So let's get our sums of squares. So remember, this is the equation for getting sums of square. The sum of x squared, meaning you square each x individually, minus the sum of x total squared, meaning you add up the total, that sum of x, plug it in there, and then square that total divided by n. And this should be really a lowercase n. This is used interchangeably, the capital N, but in this case, they're samples, so a lowercase n. So let's see how this looks. So if we were to take the sum of x squared, basically 42 squared plus 37 squared plus 42 squared plus 36 squared plus 34 squared, we would get 7,349. Doing the same thing for group 2, we would get 8,410. If you recall, our sums of x's were 191 and 204. So is what we would do is plug that in. So, we want to make sure, like, so the sum of x squared for group 1 is 191 squared. Sum of x squared for group 2 is 204 squared. So when I plug those in, I don't calculate those all the way out, but I know a lot of students do. So basically, these right here are going to go in this spot, okay? And these are going to go right here, is what they do. And this N is for how many are in each of the samples. So this is going to be 5 for both of them. It's not 10, it's 5. So if you look here, this is what those equations look like. Sums of squares for group 1, 7,349 minus, this was that sum of x total squared, 36,481 divided by 5. So we end up with the sums of square for group 1, 52.8. Sums of square for group 2, we get 86.8. And that's why I put the little subtext, group 1 versus group 2, just so you can keep them organized. So now we have our sums of squares so we can actually get our pooled variance. This can be kind of lengthy. The problem is like we're at a step where we can actually test that homogeneity of variance. So if you recall, several slides back, I talked about homogeneity of variance. That's that assumption that the variances will not be significantly different. And for that is what we want is our HOV, which is also known as an F max, but I am happy to just call HOV. You want this to be less than 2, and in this case, it is less than 2. But how did we get these? Right here, our variances. So we're going to take the larger variance and divide it by the smaller variance. Okay, so I'm going to go back one slide. So if you notice 52.8, let's find the variance. So 52.8. So I'm calculating variance divided by degrees of freedom, right? Because variance, the equation for variance is sums of square divided by degrees of freedom. 52.8 divided by 4, right? And if we calculate that, 52.8 divided by 4, it's 13.2. Okay. Now the variance for group 2 is 86.8 divided by 4. So 86.8 divided by 4, that's 21.7. So this is the larger variance. So this one is going to be the one that goes in the numerator on top. So as you'll notice, that is the one. This is the larger one. 13.2 goes on the bottom. So the smallest is on the bottom, the largest is on the top. If this is less than 2, then we can say that our homogeneity of variance was met. It was not significantly different. If it's larger than 2, then we know at this point that our results are probably going to be invalid. We'll still report results, but we can know that homogeneity of variance probably impacted our ability to find patterns in the data. So now that we've met homogeneity of variance, we can continue with our pooled variance. So we use those sums of squares, as you can see, 52.8 plus 86.8 in the numerator, and then divide by the sum of the degrees of freedom. Again, this is where I would put parentheses so that you make sure your order of operations in your calculator is effective. So our pooled variance is 17.45. That's the pooled variance. That's basically the weighted variance is what that is, that pooled variance. So now we can move forward and calculate that estimated standard error of the mean difference. So if you'll see, this is pooled variance, this is pooled variance. The reason why there's two is because you can actually have different sample sizes with independent t-tests. I will never give you different sample sizes, but you can. So in this case, it's 17.45 divided by 5. And this is probably where I see students make the biggest error. Your degrees of freedom should only be used in the variance equation. So let's go back. This is a form of variance, the pooled variance. So we're using the degrees of freedom here in the denominator. We do not use the degrees of freedom in the error equation. So if you remember, previously, error was for the one sample t-test, it's the standard deviation divided by the square root of n. This is sample size, not degrees of freedom. Just like these are sample size, not degrees of freedom. Most common error I see students make is accidentally put degrees of freedom there. Again, these are two separate fractions being added to each other. So it should be 17.45 divided by 5 plus 17.45 divided by 5, and then take the square root. One way that I do that when I put it in my calculator, I do, especially because it's equal sample sizes, I just do 17.45 divided by 5 times 2, because you're adding those two together. So times 2, and then take the square root of that. So your error, it would be 2.64. Now we have everything we need to calculate that test statistic. So we had our mean differences at the top, 38.2 minus 40.8. Here's our error, 2.64. Here is our test statistic, negative 0.985. Not very big. It's not even one standard deviation from the mean. So let's continue step 3 because we still need to calculate an effect size and a confidence interval for this test. So we will need to calculate an effect size, and we can choose either to do a Cohen's d or eta squared. Remember, Cohen's d is the number of standard deviations that the sample mean shifted from the population mean above or below the population mean, independent of the sample size, and it's based upon the null. So it's basically how many standard deviations did the independent t-test increase or decrease from no difference or 0. And eta squared is that proportion of variance in the dependent variable that's due to the independent variable. So there's two different calculations. Cohen's d is going to differ with independent t-test. We're still going to use the mean difference in the top, so that numerator is the mean difference. But now we're going to use the square root of the pooled variance. Basically, if you recall before, our Cohen's d was the mean minus the population mean divided by the standard deviation. Remember, standard deviation is the square root equals the square root of variance. So this is variance right here. So we're taking the square root of variance. So it's basically the pooled standard deviation is what this is. Pooled standard deviation is what that is, as you can see. So we would take that 17.45 and plug it in there and take the square root of that and divide it into that mean difference. So we would get a Cohen's d of 0.62. Another big error that I see is people forgetting to take the square root right here. You have to take the square root. Otherwise, you're dividing by the variance and not the standard deviation. Now we can look at eta squared. Sorry, I don't know why it's only on one side. So eta squared again is that percentage or proportion of variance accounted for by the treatment effect. And it's the same equation as it was for the one sample t-test, but now the degrees of freedom is not just one sample, it's the combined. So it's the same degrees of freedom that you use to look up your critical boundary. So degrees of freedom for group 1 plus degrees of freedom for group 2. So in this case, it's our T obtained. So again, the obtained test statistic. But because these are negative, if you just put it in your calculator as negative 0.985 squared, it's going to show a negative 0.97, and that's wrong. So just when you're squaring a negative, just drop that negative, and is what you should be getting is 0.11. This is another example where I would put parentheses around here, this. So when you enter this in your calculator, this is how I would enter it. 0.985 squared divided by 0.985 squared plus 8, and that's in parentheses. So I would not even put the negatives there because that will throw it off. So then you should be getting 0.11. And is what this means basically is that 11% of the variance in the dependent variable, which is depression, can be accounted for by their treatment condition or the treatment. So let's talk about confidence interval. Now, if you remember, confidence interval is the range where the population parameter would fall if the null is true. So range is two different numbers. So if you recall, we had this originally was a one-tailed test. But because we're looking for a range in numbers, we need to use a two-tailed critical value for the confidence interval. So I provided all of this information. So now we have to use the two-tailed just for the confidence interval, always. So always two-tail for confidence interval, because we need that range. If you did a one-tail, it would only give you one number. We need the range, the complete distance from the lower value to the upper value. So we know that our alpha level was 0.05, which is a 95% confidence interval. So 95%. We're going to find the critical value for a two-tailed test with the degrees of freedom of 8, because that's the combined, should be getting a critical value of 2.306 in that table. So the first thing you want to do is what I do is I usually multiply these two together. So that's your estimated standard error times the critical value for a two-tailed test. And this is the difference between the sample mean for group 1 and sample mean for group 2. So in reality, it's going to be, so 38.2 minus 40.8 is negative 32.6. So this is 32.6, that difference. And then I just do 2.306 times that 2.64, okay, because that 2.64 was our estimated standard error, like was the denominator in our original equation. So I put them all up here. And for that, I get 6.0878. So basically it's plus or minus, right? So 32.6, or I'm sorry, it was negative 32.6, right? Let me redo that, 38.2. I don't know why it doesn't sound right to me. It does not sound right. Minus 40.8, yeah, negative 2.6. See there? We're going to scratch that out. So it's just negative 2.6. I don't know what I was thinking. So negative 2.6 minus 6.08 and plus 6.08. So here is what we get. our confidence interval. Negative 8.69 is the lower boundary, and 3.49 is the upper boundary. And in reality, if we're looking at this, if we look at the distribution, the bottom, the lower mean is negative 8.69. The upper is 3.49. 0 falls over here somewhere. And 0 is our H of O, our null. There is no difference. So because 0 fell in between here, we know we're retaining the null. If we rejected the null, 0 would be on the outside of those somewhere. So let's look at how we report this. So again, I used Cohen's d because it's the most common. You're okay if you use eta squared, but Cohen's d always gives you a higher probability of points, because if you get your test statistic wrong, that t obtained wrong, then your eta squared's wrong. I've seen people get their test statistic wrong, but then get Cohen's d correct. So that's more points, higher probability of points. So we did not find significance. So we have the new therapy, and I always include the mean for that group. Did not significantly decrease depression more than traditional cognitive therapy, and then I provide the mean for that. As T, our test statistic is negative 0.985, and we always include our degrees of freedom here that we use to look up the critical value. We know P is greater than alpha because it's not significant. One tail test originally, our effect size was 0.62 or negative 0.62 in reality, but if you drop that, that's fine. And then we report 95% confidence interval, because 95% coincides with a 0.05. 0.05 is split in half into the tails. All of the middle is 95%. So it's important that all of this is included in your APA results. So hopefully that helped. There will be more videos available for you, like shorter clips to help you through the process. And again, please reach out to me if you have any questions. I'm happy to help you.